Very good afternoon to all. Welcome to the final session of the final day. Today's speaker is Dr. Maheshwara Velluri. Dr. Maheshwara Velluri is an associate professor at School of Mathematical and Computing Sciences, Fiji National University. He obtained his PhD from Krishnadevaraya University, India, and was a visiting researcher at University of Auckland. His areas of interest include computational number theory, computational algebraic geometry, and cryptology. Dr. Maheshwar Rao is a member of International Association of Cryptographic Research, American Mathematical Society, and the Institute of Mathematics and its applications. He served as head of School Mathematical and Computing Sciences and Associate Dean at the College of Engineering, Science, and Technology, and is also an elected representative of the University Executive Council. He has served as technical committee member of several international conferences and a reviewer of international journals. He had received Best Paper Award for his quaternion encryption work from World Congress on Industrial Control System Security 2016, London, UK. Today, Dr. Maheshwara Rao is going to talk about quantum computing changing the cryptogram. Over to you, sir. Now I request the speaker to deliver a talk on quantum computing changing the cryptogram. Over to you, sir.
Thank you, madam, for your nice introduction, kind introduction. I would like to give talk on quantum computing, the changing cryptogram. I would also like to thank our Department of Mathematics, MS Ramaya Institute of Technology, Bangalore, India, and other members and friends who were in this opportunity. I would like to thank cryptographers and mathematicians and a few organizations because I'm using a lot of their stuff in this talk. Whitefield Diffie, Martin Hellman, Rivest Samir, Edelman, Elgamal, Neil Kobridge, Victor Miller, and so on. NIST, IBM, Google, and Paul Bioff, Richard Feynman, Bennett, Brushard, Peter So, Laugrova, Mayers, and Yo Kent. In my view, the basic requirements in human life are privacy, security, and trust. In this talk, I focus more on security. People always confuse what is cryptography, what is cybersecurity. So if we refer cybersecurity, everyone is familiar. If we refer crypto, no one responds. I thought to give what is the difference between crypto versus crypto and cybersecurity. Crypto is the study of the principles and techniques for secure communication in the presence of third parties called adversaries. Whereas cybersecurity is the practice of protecting communication and computer systems from the digital threats, attacks, or damages to their data, hardware, software, etc., as well as disruption or misdirection of the service provided by them. Cybersecurity relies heavily on the cryptographic algorithms. Cryptographic algorithms like AES, RSA, ECC, and SA3 are the most popular, used to protect emails, credit card information, iCloud data, corporate data, as well as to build security layers, etc. The design of the cryptographic protocols relies heavily on the computational or mathematical problems, means that computationally expansive has to be essentially impossible on a conventional digital computer. So mostly we use mathematical problems, NP type problems. Before I give further, I want to show Google website. You can see that HTTPS, S stands for SSL certificate. This is a digital certificate. If you don't have this digital certificate, easy to hack any website. Look at any organization, your MS Ramaya Institute of Technology website itself, you can see that if it has HTTPS, if you have that, so that is secure because we have SSL certificate that protects the website. If you don't have that, we don't have SSL certificate, easy to crack the website. So this is just an example where we can use cryptographic protocols. Security features and purpose of crypto. Crypto provides the following standard security features. One is confidentiality, integrity, authentication, non-repudiation. Let me give the meaning of these terminologies. Confidentiality means which assures that information can be viewed by unauthorized person. Sorry, cannot be viewed by unauthorized person. Integrity, which assures that information is not altered without your knowledge. Next, authentication, which assures that people you deal with are not imposters. Then non-repudiation assures that author cannot successfully dispute his or her authorship, the validity of an associated contract. That means that once, say for example, once you send email, then you can't decline that I have sent that email because that non-repudiation property serves that purpose. We have mainly two types of cryptographic protocols or algorithms. One is private, two types of encryptions. One is private or secret or symmetric key encryption. In the symmetric key encryption, we have two players. One is sender, another one is receiver. Say, for example, if I want to send a file to you through internet, anybody can read that file. What I do, I encrypt the file using a key. Then you can receive the encrypted file. In order to decrypt the file to obtain the original message, you need to use same key. So what I need to do, I need to save the secret key with you so that you can be able to decrypt the file. So that system is called the symmetric key crypto system because we say the key. So this is the framework of symmetric key crypto system. Next, let us recall codebreaker Alan Turing, who broke German cipher Enigma mission during World War II and saved over 14 million lives. So this is the Enigma mission. You could save over 14 million lives by breaking the Enigma mission. Then let me give private key cryptography. Private key systems that uses a single key, as I mentioned before in the framework, that both the sender and receiver have. This algorithm provides only confidentiality of information or data. We have few famous private key algorithms. One, you can see that Enigma mission itself is a symmetric key crypto system which uses symmetric key encryption. And AES, advanced encryption algorithm, DES, data encryption algorithm, triple DES, 3 times of DES, Blowfish, Twofish, Salsa 20, MAC, message authentication code, etc. These are the few symmetric key crypto algorithms. We do have another one is hash function. Hash function we use for integrity of the message. What is hash function? Hash function that maps data of arbitrary size to a bit string of fixed size. Precisely how we express in terms of mathematics, if you take a function h, which takes the binary data of unknown size, then it generates output, the k-bit size of output. Few of the hash algorithms, we use MD5, message digest 5, SHA-1, secure hash algorithm 1, SHA-2, but I haven't listed here, SHA-3, secure hash algorithm 3. These are the few famous hash algorithms. Another type of crypto system is a public key crypto system. In the public key system, crypto system, we use two keys. One is public key, another one is private key. Let me give a bit background of a public key crypto system, then we can discuss later how it works. This idea proposed by Merkle, Diffie-Hellman, who received Alan Turing Award in 2015 in the year 1976. These two gentle guys, these are very famous because they opened door for secure crypto system in the public domain. This idea was also proposed by James Henry Ellis at the Government Communication Headquarters, GCHQ, UK in 1970 under the name of non-secret encryption, but it was not disclosed until he died, I think in 1998, sometimes they disclosed. But same idea was proposed by this James before Diffie and Hellman. Then few public key algorithms. One is RSA, R is missing, sorry for that. Another one is ECC, Elliptic Curve crypto system. Another one is Mackey-Hellis encryption, Merkle hash tree signatures, Merkle-Hellman snapshot encryption, Buchman-Williams class groups encryptions, and further we have ECDA, Elliptic Curve digital signature algorithm, NTRU, nth order truncated ring unit, LW, learning with the errors problems, ring learning with the error problems, SIKE, CSIDS, these are the isogeny based systems over elliptic curves. Then what is, in order to provide security, we use computational log problems. Let us recall the discrete logarithmic problem over a finite field. So I think you know what is a finite field meaning. It is a mathematical algebraic structure which has certain algebraic properties. So we take here, let G be a subgroup of field, or you can take finite field of order P is a prime, or elliptic curve over finite field of order P, where we choose in practice P value roughly 1024 bits length, which is a prime number. Given G belongs to G and Y belongs to G such that Y equals to G power X means if you multiply G X times, you will get G power X. Then you take a remainder by dividing by prime number P. Then you will obtain a Y value. So when I give a Y value and I give a G value and P value, computing X value is odd even for computer. So this is called discrete logarithmic problem, and the computer also can't solve this problem, even this classical computer. So how we use Diffie-Hellman, discrete logarithmic problem in a crypto? Let me give Diffie-Hellman key exchange protocol, which was proposed by Diffie and Hellman in 1976. So we take a system parameters, a finite field FQ, and a primitive G, which is belongs to a finite field. Take P equals to a prime number. I have taken 40961. G is a primitive, which is 237. Then Alice chooses a random secret key XA 3243, which is within the domain of GP, right, or FE, and sends YA equals to G power XA, which gives 34,605. This is the Y value. So what is G value? You can use G value, you can use this P value, then this is secret, 3243 is secret, or secret key of the Alice, and it generates public key 3465. Then Bob chooses similarly a secret XB, which is 6,734, and computes the public key of the Bob using the discrete logarithmic problem. We can obtain 40,504. This is the public key of this. Then they both exchange. Both the public keys can be exchanged. So see, Bob sends YB value to Alice. Alice sends YA values to Bob. Then they can compute, Alice can compute KA equals to YB. This is the public key of the Bob, and using private key of the Alice. So then they can obtain 8,697. Similarly, Bob can compute KB value. He can obtain same value. See, without sharing the private keys of Alice and Bob, they are able to come up with a common shared secret key. This solves the exchanging secret key in the symmetric key crypto system. This is the advantage. So if you have any confusion, just I give one real-time example. What is public key? What is private key for layman language? When you have email system, you have password that acts like a private key, and you have username like email ID that acts like public key. Email password is like a private key. Email ID is like a public key, right? So this is the framework of public key crypto system. This is how we exchange emails. So we have plain text and ciphertext, sender, receiver. You can see that sender has a plain text, a message. Then in order to send encrypted message, the sender uses receiver's public key. You can use the receiver's public key because public key means username, right? So email ID. If I want to send a message to you, I need your email ID. That is public key. Then I can encrypt and send it to you. So in order to decrypt means that in order to open your email inbox, you need to have your password. Then you can be able to open it and you can see my email, whatever I have sent to you. So that's how the public key encryption system works. So the famous public key crypto system is RSA public key crypto system, which was proposed by Ron Rivest, A.D. Samir, and Leonard Edelman in 1978. They were that time working at MIT. Then the same scheme was also invented by Christopher Cox at the Government Communication Headquarters, GCHQ, United Kingdom in 1973. So you can see that publishing the idea is more important to get famous. These guys invented before RSA people, but credit went to RSA guys, same idea. So it relies on the relatively easy of computing large primes and the comparative difficult of factoring integers for its security. What does it mean in simple language? I can give you. If you have two prime numbers, one is P, this is a large prime number. I think it has roughly 512 bits, 512 bits length. This is the integer. When we convert, you can convert it log P base 2 plus 1, you can use it. It will give the length of the prime number in terms of bits. So similarly, you can take another prime Q, it also roughly 512 bits length. Then when you multiply these two, you can easily multiply these two. When you multiply, you can get large composite number, which is n equals to PQ. So this, if I give here, the computational odd problem is, if I give the n value, we don't know what are the P and Q. If I ask you to find P and Q value, very hard to ask. For small values, we can easily find it. For large values, very difficult. Even for computer, it takes millions of years. So that's how security relies. Security relies for RSA based on the integer factorization problem. Now, we have few methods to factorize an integer. Let me give a method which is called difference of squares. If n equals to pq is a composite, then we can easily find factors by n equals to, we can take two numbers, x square minus y square, which you can factorize as x plus y times x minus y. We factorize n equals to this number, it's a large number, by looking an integer y such that n plus y square is a perfect square. So I have taken few steps here. So first, when we take 1 square, which is not perfect number, then 2 square, not perfect number, and so on. I have taken list of, keep on going. When I reach to 12 square, I could see that perfect square. So this is a perfect square, then one value, it acts like a x square value. Then you can see, we know y values because we know n value, we know y value, we have been choosing y value, then we could get x square value. If you know x square value, then you know already y value, then you can factorize it. So it gives x value, y value. Then you can see for this number, p equals to 13,567 and q equals to 13,591. These are the two prime numbers when you factorize this n value. Then another method, Pollard's row, row minus 1 method. Pollard's row minus 1 factorization method was invented by John Pollard in 1974. The method works as shown in the following algorithm and requires 2n log n base 2 steps. So this is a computational complexity. How it works, you take input value n equals to pq, that to be factorized, set a value a equals to 2, then use loop, keep running the loop where certain bound is coming, then you obtain a b value, then find GCD between n and b minus 1, you can find a c value. If c value is in the bound 1 less than or equals 1 less than c less than n, then successful return c. Then increase j and loop again at steps 2. You can keep on continuing until you get appropriate c value that gives one of the factors, then you can find it, another factor. I have taken an example for this. I have taken n equals to this number, a equals to 2 small number, then 2 square we know, then we don't obtain any GCD here. It's only 1, so that means it's not appropriate factor. 1 is trivial factor. Then you can see that you can keep on multiplying it in a exponential factors. You can see in this example. Then when I have taken 2 power 10 factorial, you can see that value we obtain 401. So non-trivial factor, then we can find by dividing the given number by 401, we can obtain another prime number. So this is how we can use Pollard's row method to factorize a composite number. Now, let me give algorithm of RSA, how it works. Simple, but very beautiful algorithm. Many of the applications, even whatever we are using, Zoom, perhaps they might be using this algorithm. Generate 2 random prime numbers. In practice, we need to choose minimum for base, lower level. Now we use 104 bits, 24 bits. For high level of security, we use 4096 bits. But I have taken small numbers here to demonstrate how it works. P equals to this a prime number, Q equals to another prime number. Then when you multiply 2 prime numbers, we can obtain composite number. Then we also compute Euler-Taussian function, which is P minus 1 times Q minus 1, which gives this. You can notice the importance of Euler-Taussian function. The security relies here, right? So why? I can show you. Then choose a random E, that this E acts like a public key. So we have to choose this E value within this range, 0, 1 less than, E less than Euler-Taussian function, such that GCD of E and pi n Euler-Taussian function must be 1. Then only you can be able to find it, the inverse, that inverse of E, that is D. That is, D acts like a private key. Compute D equals to this number such that E times D congruent to 1 mod Euler-Tolchian function. So look at this. If you know factors, you can find easily Euler-Tolchian function. If you find Euler-Tolchian function, you can easily find private key D, because you know public key. Simply 1 by E inverse of Euler-Tolchian function will give you a private key, that is secret key. So we need to be careful. So we have to choose even prime numbers such a way that, like we say, 2p plus 1 form. It's our safe primes. We call safe primes, because if you don't choose it in the proper aspects, then security will be compromised even for RSA. These are the key things in security aspects. It looks like simple, but very key factors for security. Then we can obtain public key NE. These are the values. Private key, these are the values. As I mentioned, that like your email ID acts like a public key, your password acts like private key. But we don't speak that language here. In crypto, we speak private key and public key. Then to encrypt, you have a message, which is a big number. So to encrypt, simply what I have message, this is the number. I want to if I send this message as it is to you over internet, anybody can read, because it is a plain message. Because internet is a public network, anybody can read it over internet. So then what we do, we need to encrypt it. In order to encrypt, what I need receiver's public key, means receivers like a user email ID, right? So receiver's public key, we know this is the receiver's public key. If you have a receiver's public key, then we can compute simply C equals to M power E mod N. This gives the ciphertext. This is a ciphertext. Rather than sending M value, we compute this and we send this to the receiver. Once he receives this C value, then receiver should use his private key. That is, it's there in his hand. He says privately, this is public key. Public key is open to anybody. But usually we give to dedicated users, right? So then this is the public key C, public key E, then he knows is private key D, then he can do this computation to obtain original message sent by the sender. Sender is this guy. Sender sent this message, right? He can receive the original message. Next, another method is elliptic curve crypto, which was proposed by Victor Miller and Neil Koblitz independently in mid-1980s, and they worked independently. Same proposal they have, same idea they had come up. Then they both published independently 2 different papers. Elliptic curves are class of Diophantine equations, which are in short form. We express y square equals to x power 3 plus ax plus b. We know that elliptic curve crypto system is much more famous than RSA because it provides better security for smaller size keys. Then in real time now, we use elliptic curve crypto system, even Bitcoin, Australian citizenship card, even as I mentioned, SSL certificates, TLS, even particularly now elliptic curve digital signature, which is a Edward 25519, which is one of the class files of elliptic curves, which is used in TLS 1.3, SSS, Tor browser, GCAS, and even WhatsApp signal protocols, etc. We use this very famous digital signature. But ECC is not secure against quantum. Not only ECC, even RSA, even Diffie-Hellman, key exchange protocol. These are all not secure against quantum computing attacks. Now, how this ECC works? Let me give. This is just this just works like Diffie-Hellman key exchange protocol, where we use a multiplicative group. Here we are using only additive group. What is additive group? Elliptic curve is a good additive group. Here we take elliptic curve over field, where we choose usually Q value we choose 1024 bits length, which is a prime number. Then if we choose a rational point P over elliptic curve, then we can compute by adding P n times, we can obtain Q value. By adding P value, P is a point. By adding point P n times, you can obtain Q value. But we have some process here over elliptic curve. We use some technique here in order to compute this Q value. Then it is hard to compute n value. If I give you P value, which is a point, Q value, which is a point, both are points on elliptic curve, then how many times P has added to obtain Q value, it is difficult to find it. This is called a computational odd problem. So even computer can't be able to compute it. So now let me give an example how elliptic curve was Diffie-Hellman key exchange protocol and elliptic curve system, how it works. This was proposed in 1985. So we have elliptic curve y square plus x power 3 plus 7x plus 29 be an elliptic curve over this finite field. Then we have chosen a point, this point P. Sorry, this is a point over elliptic curve. It should be elliptic curve, not a finite field. So E of GP. Then Alice chooses a random secret NA, which is it in the field, and send and compute this P. The point P is added NA times, then to in order to obtain this QA point. Then this is a QA acts like a public key, and NA equals to 7345 acts like a private key. Then Bob also chooses a secret NB, which is a 435, and computes this value QB. This is the point, and they both exchange QA value, QB value. These are the public keys and can be exchanged through public network. After exchanging through public network, they compute this NA is secret key of the Alice, and QB is the public key of the Bob. Then if you add public key of the Bob NA times, we can obtain this point. Similarly, Bob receives QA, that is public key of the Alice, and using his private key NB, he adds QA NB times, then you can obtain this point. You can see that these two are the common shared points which are secret. This is called shared key between Alice and Bob. This is how key exchange protocol works. So this has a lot of applications in even web SSL certificate. Everywhere we use these protocols. Right. So as I mentioned that these are all based on number theory. Most of the number theory based crypto systems are threatened by quantum algorithms. What is quantum algorithm? Let me give a bit background about quantum computing. What is quantum computing? Quantum computing. Digital computers today are not that efficient as universal computing devices. They have limits to do certain computational tasks. Alternatively, we have quantum computer. It's a computational device that makes direct use of quantum mechanical phenomena such as superposition, entanglement to perform operations on binary data. In this quantum computing, we call quantum bits, qubits. In a classical computer or a digital computer, we call bits. It also uses quantum mechanical effects such as quantum communication and quantum computation to perform certain tasks. A big background, historical background of quantum computing development. In 1970, Paul Benioff described first quantum mechanical model of a computer. In 1982, Richard Feynman, Nobel laureate in physics in 1975, suggested to build quantum computer based on quantum mechanics. In 1985, DS challenges polynomial time Church-Turing thesis. In 1995, quantum circuits given by this Solovay-Kittai theorem. In 1997, Bernstein, Vazirani, universal quantum Turing machine. These are the developments in underlying technology of the quantum computing. The displayed picture is the IBM's 53 qubits quantum computer. I acknowledge IBM for their pictures. Let me give the process of quantum computation. We have Hilbert space. If you are a mathematician, you can easily understand. Finite dimensional vector space over the complex numbers. Then, which is just a spherical shape, right? Ball sphere. A physical system is represented by an n-dimensional Hilbert space. You can represent this by n-dimensional space. The state of the system is a unit vector in the Hilbert space, which is denoted by a wave function, ket. We represent by ket xi. For n equals to 2, we use the vectors. We can see that you can use the vector ket 0, 1, 0, and ket 1, 0, 1. This we call this qubit 0, qubit 1. So these are the vectors. Form a basis of the Hilbert space. So a qubit is a vector which we represent a times qubit 0 plus b times qubit 1, where a and b are complex numbers, and mod a square plus mod b square always 1. When measured, mod a square is a probability to get 0, and probability b square, mod b square, the probability to get 1. So note that n qubits equals to 2 power n classical bits. This gives that how fast the quantum computer. Look at that. We have in the we have qubits of 32 bits or 64 bits. If you take 34 bits means 2 power 5. 64 bits means 2 power 6, right? So this is just simply 6 qubits. Very simple. So that's why the quantum computer is exponentially faster, whereas classical, you can relate a classical computer and quantum computer, the speed by using this relation. n qubits equals to 2 power n classical bits. Similarly, we have used only 1 qubit here. If you want to use two qubits representation in the Hilbert space, we express by tensor product. So Kent xy equals to Kent x of tensor product Kent y, which tensor product always gives exponential. So this is the representation for tensor product of 2 bits, which if you multiply 2 times, if you multiply by tensor product 2 times, then we can get this. Like we have Boolean circuit for classical computer. Similarly, we have quantum gates. In a classical computer, we have Boolean gates, right? So similarly, like a Boolean gates means we have negation gate, XOR gate, OR gate. So we have on classical computer. Similarly, we have quantum gates. Let us recall few important quantum gates. We are Pauli XYZ gate, X this 0, 1, 1, 0. It is in terms of matrices. And Y gate, G gate, and T gate, Adamant gate, and also you can see how Adamant gate acts. If you take a qubit 0, if you apply Adamant gate, then you will get superposition of qubit 1 and 0 plus qubit 1. Similarly, if you take a qubit 1, if you apply Adamant gate, you can get superposition. Again, if you apply Adamant gate on this superposition, you can obtain back 1. Again, if you apply here Adamant gate on this superposition, you can obtain back this 0 qubit. So the very important feature on quantum computer is you have reversible functions, Whereas in classical computer, we can't reverse the computational process. So this is a beautiful feature on quantum computer. So control not gate, C not gate. So this is another gate. You can generalize these gates for many dimensions or many bits, qubits. We have two significant quantum algorithms which works on cryptographic protocols. One is a Peter Source, who received Nevalina Prize in 1998 for his algorithm. He proposed polynomial time quantum algorithms for integer factorization and discrete logarithmic problem. So his algorithm can break integer factorization problem and discrete logarithmic problem in polynomial time over quantum computer, but it uses both off-what on classical computer, off-what on quantum computer. Then Love Grover, Indian, I think he was alumni of IIT Delhi. He proposed polynomial time quantum algorithm in 1996 for quadratic speedup. Such algorithm, what does it do? If you take any data in a Google data, any data, if you want to trace out a particular data, you can trace out it in the quadratic speed using Grover's algorithm. So for example,
Sir, your voice is not audible. Sir, we are not hearing you.
hello.
Yes, sir, we can hear you, sir. We can hear you.
Hello.
Sir, can you hear me?
Please, can anybody respond?
Sir, can you hear me? Can you hear me, sir?
Oh, okay. Sorry for interruption.
That's okay.
Yes, I can.
Yeah, yes.
I can now.
Sir. Yeah, you can go ahead,
It's
sir.
clear.
You can go ahead.
All right, thank you. Okay, sorry for interruption. Next, we have a few elliptic versions of discrete logarithm. We can use a source discrete logarithm polynomial time quantum algorithms for elliptic curves, which was proposed in 2003. These are the significant quantum algorithms to affect cryptography. So let me give source algorithm for integer factorization problem. The beauty of the source algorithm, which can crack integer factorization problem as well as discrete logarithmic problem, and for the development elliptic version of discrete logarithmic problem, all these can be broken once quantum computer is available, and if we are able to write a program over quantum computer, which was proposed by Peter Shor in 1994. So he is my hero. Why I'm saying? Because after he proposed this algorithm, every country started investing money to build the quantum computer. Use impact on the society, use impact on technology, particularly quantum technology, to build. Every government now spending millions of dollars to build the quantum computers, because if you have quantum computers available, then we can do fast computation, then we can crack many of the security systems. So that's the reason many governments investing use money for, not only governments, and also like a Google, IBM, many D-Wave in Canada-based company. These are the companies spending a lot of money for building quantum computer. Let me give this algorithm integer, and I give only integer n. This is the runtime. This is the polynomial time. And if n is even, then return. Of course, we know that trivial factor you can find easily if it is n is even. If it is n is odd, definitely we go for next step. Determine whether n equals to a power b for integers a greater than or equals to 1 and b and b greater than 2. If yes, return a factor. We can find a factor a, factor of a. A factor of n. Next step, pick a random integer a, which is less than n, and compute GCD. If GCD equals to 1 or greater than 1, we can find a factor of n, which is easy step. But a difficult task here, finding order of an element in this field, Gn is a difficult, even for classical computer. Then Peter Shor proposed this algorithm to find order of an integer in this ring Gn using quantum Fourier transformation and quantum circuit, in which we can easily find the order of an element, which is simply a power r congruent to 1 mod n. If you obtain a power r congruent to 1 mod n, then the order of an element a is r. Now, if r is odd and a power r by 2 mod n equivalent to -1, then we have to go back to step 3. If r is even and a power r by 2 mod n not equals to -1, then we can evaluate by using GCD technique. We can find non-trivial factor of an integer. If d, either we can obtain two values, plus or minus, not equals to 1, then d is the one of the non-trivial factors of n. Otherwise, we have to go back to step 3. This is a simple algorithm I projected here. But the typical part is finding the period of an integer or order of an integer. So for which we need to use quantum algorithm. Let me give Peter's quantum algorithm. We assume that our machine has two quantum registers. One is source and another one is target. We have two. Both we represent in terms of binary form. Find a number p, a power of 2 power n, with n square less than or equals to p less than or equals to 2 power n. In this step, both source and target registers are initialized in the state 0, 0, both in terms of qubits. We put the source register in the uniform superposition of a quantums representing integer x mod b and load the target register with all zeros. So it works like one is source register, another one target register. We have two in quantum, works differently than classical computer. This leaves the mission in the form of a wave function, xi1 which equals to 1 by square root p sigma x equals to 0, x equals to 0 to p minus 1 in these positions get x get 0. Note that this keeps each qubit of source register into the superposition. Next step, we have to compute a power x mod n in the target register by applying a gate UA. This leaves the mission in this form. Further, then apply quantum fast Fourier transformation on the source register that maps x to this state. Then this leaves the mission in this state. Then we need to, in order to detect the period in a power x, we observe both get g in the source register and get a power x mod n in the target register of the mission, and measure both the arguments of the superposition for obtaining the value of get g in the first argument and sum as a response for the target register. So in the range 0 less than or less than k. Then we need to apply probability here. To extract the required value of k, we apply the concept of probability distribution as follows. Then given pure state in this wave function, the probability of different results for this measurement are given by this probability distribution. Here we can obtain. Then what we do, I am skipping this sum of calculations. Then we apply continuous function expansions. Then in order to obtain the k value, once we obtain the k value, that gives the period of an element A. Then the mission stops. So this is how it works. So this algorithm we need to run on quantum computer. Unfortunately, we don't have quantum computer in hand to run this algorithm, right? Let me give some historical background where the current status of quantum computing development. In 2013, I haven't listed few important stuff I have included here. In 2013, Aronson et al. Boston sampling as a way to show quantum supremacy. They have used the quantum supremacy word and showed some sampling. In 2016, these guys developed random circuit sampling in which instantaneous quantum polynomial time. They showed that. Again, in 2019 September, Google Artificial Intelligence Quantum and NASA published a joint paper, Quantum Supremacy Using a Programmable Superconducting Processor. And they claimed that Google's quantum computer named Sycamore had completed a task in 200 seconds that would take 10,000 years to complete on the most powerful supercomputers, that is a digital computer. You can see that how fast the quantum computer. So classical computer takes 10,000 years, same task this quantum computer could do in 200 seconds, how fast you can assume now. Recently, I have picked this from this magazine. In July 2021, recently, a team in China has demonstrated that it has the world's most powerful quantum computer, leapfrogging the previous record holder, Google. So this shows that quantum computer is about to come in the next few years. I don't think so. It takes more than 5 years. For certain applications, probably it may take for long to build the source algorithm for dedicated quantum models for writing Peter-Source algorithm, because Grover's algorithm we can run on few models, but Peter-Source algorithm is a challenge to write a code on certain models of quantum computing, because a lot of noise in quantum models, because quantum mechanics has a uncertain Heisenberg uncertainty principle, which is difficult to build a quantum computer if you reduce the noise. But to build reduce the noise, we can easily build the quantum computer. But scientists have been trying using some coding techniques to reduce the noise to build the successful quantum computer.
Sir, your voice is not audible. Sir,
there are some audio issues at the speaker's end. So just bear with us for some time and we'll try to sort it out. I'm sorry for the network issues that the speaker is facing. He's not able to log in, so just give us some time. We are facing some issues which are not getting resolved. So what we will do is, if the speaker joins, we will record the whole thing and you can watch it later on YouTube. I'm sure all of you have the YouTube link with you. So the talk will become accessible in YouTube to everybody. About the certificates will be ready by next week. So please make sure that your name that you have entered in the Google form is correct, because it is going to appear in the certificate as it is. And I also hope that all of you have filled up the Google forms after each session for you to be eligible for getting that certificate. We will then wind up this session. And as I said, the talk will become available to you if we are able to record it fully. Otherwise, whatever we've had so far will anyway be available. I now request Sushma to conclude the session and propose a vote of thanks.
Thank you, ma'am. It is my privilege to propose a vote of thanks for the 5-day webinar event on mathematical developments in cryptography, hosted by Cryptography and Data Science, hosted by the Department of Mathematics, RIT. I, on behalf of Department of Mathematics, Ramaya Institute of Technology, extend a hearty gratitude to all our distinguished speakers for sharing their work, knowledge, and experience with all of us. I would like to thank our honorable management for their continuous support in all our academic activities. I also thank our respected principal, Dr. N.V.R. Naidu, for encouraging to conduct academic activities in the college. I would also thank our beloved HOD, Dr. N.L. Ramesh, for his motivation, guidance, and moral support. I'm happy to express heartfelt thanks to my colleagues who made this webinar a grand success through their participation and dedication. I also thank all the participants who have participated and made the event a success. Finally, I thank all those who were directly, indirectly helpful in making this event a grand success. Thank you one and all.